Okay, 2.61 is sort of a sneak peek into chapter 3 in that we start introducing matrix equations. So if you remember, most of the problems we did in the earlier sections for this chapter involved a lot of systems of equations. Typically we have to set up multiple systems, especially for piecewise potentials, where we have to connect them via constants, a, b, c, d, e, f, etc., and then we have conditions, boundary conditions, that tell us different equations that these constants have to satisfy, and then we have to solve the entire system of equations in order to get those constants. And it got very painful very quickly. I believe the most difficult one involved solving a system that had 6 different coefficients, a, b, c, d, e, f, because it was a piecewise of 3 different sections. So that's obviously not fun to do, and hopefully if you have the mathematical background you're supposed to have in order to actually understand this level of physics, you would recognize that sort of introducing linear algebra and introducing matrices or matrices would make our lives significantly easier. And as chapter 3 is going to point out, it is actually much more natural to use linear algebra in quantum mechanics. And it's typically canonically stated that linear algebra is sort of the most natural language for quantum mechanics, and it sort of makes all of the very difficult things we've been encountering so far significantly easier to do, and in most cases almost trivial. The explanation for how this problem is set up is pretty long, so I feel like it's worth going over it at least. So I'm going to start by sort of summarizing this the best I can. So this is not exactly how we're going to set up equations down the line for chapter 3, but this is a pretty good introduction to it, in that basically Griffiths is saying, okay, so typically you have an x and a v axis, and you have your wave function looking something however it does in this region. So what Griffiths is saying is, okay, instead of trying to calculate the Schrodinger equation in its entirety, let's instead split this interval into smaller subintervals. So instead of going from, x equals negative a to x equals a, or x equals 0 to x equals a, depending on how your well is shifted or blah, 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 I'm instead going to define my x-axis using equally spaced intervals I'm going to call delta x. So this is my x-axis, and I'm going to say that this is, xj, this is going to be xj plus 1, this is going to be xj minus 1. I can go on, I can say, xj plus 2, xj minus 2, so on and so on. Each of these intervals are evenly spaced, and I'm going to call them delta x. And the wave function at any given interval point is going to be, psi j, this is going to be psi j plus 1, this is going to be psi j minus 1. And the ultimate idea is that as delta x goes to 0, we can find the exact form for psi j. So basically this is just an approximation of what the wave function actually is, and we're doing it by splitting this into intervals and only considering at each of these interval points instead of the entire wave function as a continuous whole. And in this case, if we do it this way, the derivative is going to be d psi by dx. So remember, this is psi, this is the change in psi over the change in x. So this is going to be psi final minus psi initial over the change in x. And if we think about it that way, well, we can write this as, so suppose we want the derivative at j, then we can do j final, which is going to be psi at j plus 1, minus the initial, which is psi at j. So this is going to be psi j plus 1 minus psi of j over delta x. Alternatively, if you want, you can also do psi j minus 1 instead. So looking at the interval in this region instead of sort of the interval in this region. But it doesn't matter, and Griffiths chooses to do it with the interval in this region, so I'm going to do the same. And this derivative is now our new definition for d psi by dx. And in that case, the second derivative, d2 psi by dx squared, is going to be d psi by dx final minus d psi by dx initial. So we need 2 derivatives now. So let's call the derivative in this region d psi by dx final. And let's call the derivative in this region d psi by dx initial. So that way their difference is going to give us d2 psi by dx squared directly at psi j. So in that case, this is going to equal, the final is going to be what we just found, which is psi j plus 1, psi j plus 1 minus psi j. And then this is going to get subtracted by the derivative from j and j minus 1. In that case, the final is going to be psi j minus psi j minus 1. And this is all over delta x. And then if we want to write this out further, d2 psi by dx squared is going to equal the two psi j's combined. We get psi, that is a bit of a messy psi, my apologies, psi j plus 1 minus 2 times psi j, and then added with psi j minus 1. And my apologies, I just realized this entire thing has to be also divided by the change in x. So let's just make this a little bit smaller. Close this in parentheses and divide it by delta x again, because it's supposed to be the change in the derivative of psi with respect to x. So in that case, we're going to have a delta x squared over here. And we divide this by delta x squared. So then we can then plug this back into the Schrodinger equation, because remember the Schrodinger equation is negative h bar squared over 2m multiplied by d2 psi by dx squared plus v times psi is equal to e times psi. So if we want to analyze the Schrodinger equation at each of these individual intervals, then at, for example, x sub j, we would have negative h bar squared over 2m multiplied by our new expression, psi j plus 1 minus 2 psi j plus psi j minus 1 divided by delta x squared. And we're going to add this to the potential at point j, so vj, times the wave function at point j, which is psi j. And this is equal to the energy, which stays the same because the energy is, constant, regardless of at what interval point we look at in our wave function, times psi j again. And if you want to rewrite this to make it a little bit neater, you can rewrite it as negative lambda psi j plus 1 plus 2 lambda plus vj times psi j minus lambda psi j minus 1. Whoops. And this is equal to e times psi j, where lambda is just a rearrangement of variables that's equal to h bar squared over 2m times delta x squared. And basically, from this point, what this part is saying is that the number of intervals you decide to split your sort of wave function into is going to determine the number of equations you have. So if I split my interval, for example, if I split my x, so let's say that it's, some sort of potential well that looks something like this, maybe for v, and this is from like 0 to a. If I split this interval into 2 points, then I'm just going to have a single equation. But, if I split it into like 4 points instead of 2, or actually, let's do like, 1, 2, 3. Yeah, if I split it into 4 points, I'm going to have more equations, because this is going to give me a new equation for every interval I add. So because of that, this allows us to set up a matrix equation like this. And that's actually what part A is going to ask us to do, is we're going to be asked to use this new formula to set up a system of equations for our infinite square well with 3 parts, or with 3 sort of variations, where variation 1 is that we split our infinite well in half, variation 2 is we split into 3 equal parts, and variation 3 is we split it into fourths. And we're going to see that in each case, as we go up, we get an additional new equation each time, and our resulting matrix is going to get bigger, and our sort of vector is also going to get bigger. Okay, so for part A, we are asked to do what we just talked about, but for the infinite square well. So immediately, I'm going to write out the Schrodinger equation for the infinite square well, which is going to be 2 psi by dx squared is equal to negative 2me over h bar squared multiplied by psi of x. And my initial conditions, or my boundary conditions, are going to be psi of 0 is equal to 0, and psi of a is equal to 0. So this is just a square well that goes from x equals 0 to x equals a. Now, the first thing I'm going to do, or the next thing I'm going to do, I suppose, is I'm going to take my d2 psi by dx squared. I'm going to substitute in the new method that we just got from reading the introduction, which is that d2 psi by dx squared can be rewritten in terms of this new interval notation as psi in the interval j plus 1 minus 2 psi at j plus psi j minus 1. And then this is all divided by delta x squared, and this is now equal to negative 2me over h bar squared times psi in the jth interval. And now my new sort of initial conditions, or my boundary conditions, are going to be psi at j equals 0 is equal to 0, and psi at j equals n plus 1 is equal to 0. Because remember, from the very introduction here, we are sort of splitting our integral, or not, sorry, not our integral. We are splitting our interval, or we're splitting our infinite square well into n plus 1 equal components. So if we do that, then the n plus 1th level is the very end of the well, and j equals 0 is the very start of the well. So these are our new boundary conditions. Now, what we then do is we can replace delta x, because remember, delta x is sort of the space in between our intervals. So if we have, n plus 1 total spaces, right? Because if this is, this is j equals 0, this is j equals 1, and then all the way over to like j equals n plus 1, which is the very end of our interval, then the total number of intervals is going to be a divided by n plus 1 splitting, because n plus 1 is the total number of points that we have, and a is the original length of our well, so we're dividing it in that way, and this is equal to delta x. So if we substitute this in, then our equation from up above is going to change to n plus 1 squared times h bar squared over 2ma squared times negative psi j plus 1 plus 2 psi j minus psi j minus 1 is equal to e times psi j. So I've just moved everything over to this side and then redefined delta x squared. And at this point, now we can start plugging in. So let's look at the n equals 1 case. So if n is equal to 1, then we are splitting the well into, n plus 1 is equal to 2 equal parts. So if we're doing this, then our well becomes, this is x equals 0, and this is x equals a, then we're splitting it right down the middle like that. So this is going to be j equals 0, j equals 1, and j equals 2. So then if we substitute this in, then we get n equals 1, so this is going to give us, let's see, 2 squared times h bar squared over 2ma squared times negative psi j plus 1 plus 2 psi j minus psi j minus 1. And this is equal to e times psi j. The 2's cancel out. We get 2 h bar squared over ma squared times negative psi j plus 1 plus 2 psi j minus psi j minus 1. And this is equal to e times psi j. And for this case, j can only equal 1. Because remember, for every value of j, we have to go 1 above and 1 below. So for j equals 1, we go 1 below to j equals 0, and 1 above to j equals 2. If j equals 0, we can't have j equals negative 1. That doesn't make sense. And if j equals 2 or higher, we're going to get, this is going to be negative psi j3 or negative psi j4, which doesn't exist in this interval. So j equals 1 is the only possible valid value for j in this n equals 1 case. So if we plug that in, we get 2 h bar squared over ma squared times negative psi j equals 2 plus 2 psi j equals 1 minus psi j equals 0. And this is equal to e times psi of j equals 1. And immediately, because of the fact that there's only a psi j equals 1 over here, that instantly tells me that psi of j equals 2 and psi of j equals 0 are both equal to just 0. So because of that, we have 2h bar squared over m a squared is equal to e times psi 1. Finally, oh, whoops, sorry. I just realized I forgot to include on the left side the 2 psi 1 term. Okay, finally, if we want to write this in matrix notation, in this case it's a little bit trivial because we only have one equation, so the matrix is just literally just going to be 2h bar squared over ma squared times 2 times psi 1, which is just a 1 by 1 matrix, is equal to e times psi 1. Because remember, the general form that we want is way up here. If I can find it. Yeah, h times psi is equal to e times psi. So in this case, the h is going to be this thing right here, h, and this is my psi vector, which is just a 1 by 1 vector in this case, so it's a bit trivial, and this is equal to e times, once again, my 1 by 1 vector. So the h matrix is just going to be 2h bar squared over ma squared, which is a constant, multiplied by the 1 by 1 matrix of 2, just like that. Or alternatively, you can pull the 2 out and make this a 4, and just make the matrix 1 by 1 just a 1. It doesn't matter either way, it's the same thing. Now let's do it for a less trivial case, which is for n equals 2, and I'm going to edit my properties and make my canvas a little bit taller. So if n is equal to 2, then this means we're dividing into n plus 1 equals 3 equal parts. So if we look at our well, we're going to get j0, or j equals 0. And then we're going to divide into 2 equal parts. So this is j equals 0, j equals 1, j equals 2, and j equals 3. And now, if we plug it back into the top, because remember our actual formula is n plus 1 squared h bar squared over 2ma squared times negative psi j plus 1 plus 2 psi j minus psi j minus 1, and this is equal to e psi j. Then for n equals 2, then this becomes 3 squared, so this is going to be 9 times h bar squared over 2ma squared times negative psi j plus 1 plus 2 psi j minus psi j minus 1 is equal to e times psi j. And here, now j, once again, it can equal more than one thing now compared to before. Because before we only had j is equal to 1. But now, if we have j equals to 2, then we go to the left one, that's valid, to the right one, that's also valid. So j can also equal 2. And hopefully you see the pattern now. In general, j is equal to 1, 2, 3, blah, 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 all the way up to n. So for whatever our n level is. So in this case, it's 2, so j equals 1 or 2. Now, if we plug this in for each case, then we're going to get a set of 2 equations. So we're going to get 9h bar squared over 2ma squared at the front, always. And then we have, for j equals 1, we have negative psi 2 plus 2 psi 1 minus psi 0. And this is equal to e times psi 1. And then we get negative psi 3 plus 2 psi 2 minus psi 1, and this is equal to e psi 2. So this above one is for j equals to 1, and this bottom one is for j equals to 2. At this point, now, since only psi 1 and psi 2 appear in this system of equations, automatically this implies that psi 3 is equal to 0. This also implies that psi 0 is also equal to 0, because, once again, psi 1 and psi 2 are the only ones that appear in the answers. That means psi 0 doesn't appear, psi 3 doesn't appear. That also makes sense, because the boundary conditions require psi to go down to 0, right? Psi has to equal 0 at the left end, and it also has to equal 0 at the right end. So because of that, we need size 3 and we need size 0 to both equal 0. Now, finally, we can set up our matrix equation. So now we have 9h bar squared over 2ma squared multiplied by, now setting psi 0 and psi 3 both equal to 0, we get negative psi 2 plus 2 psi 1 is equal to e times psi 1, where j is equal to 1, and 2 psi 2 minus psi 1 is equal to e psi 2, where j is equal to 2. And hopefully you see that now we can just convert this into a matrix equation. So if I rearrange this so that psi 1 is always at the front, then I get 9h bar squared over 2ma squared times 2 psi 1 minus psi 2 is equal to e psi 1. And we also have negative psi 1 plus 2 psi 2 is equal to e times psi 2. And finally, if I want to convert this into a matrix equation, then I get 9h bar squared over 2ma squared multiplied by my matrix, which is going to be 2, negative 1, negative 1, 2. And this is multiplied by psi 1, psi 2, which is my new vector for psi, and this is equal to the energy E times the vector psi 1, psi 2. So that means my H matrix is therefore going to equal 9h bar squared over 2ma squared times 2, negative 1, negative 1, 2. Now, finally, for n equals 3, same thing as before. So let's set up our equation here. I'm just going to copy and paste this. So now we're splitting this into 4 equal parts. So in this case, if n is equal to 3, then we get 16 h bar squared over 2ma squared, or simplifying this, this is just 8 h bar squared over ma squared, multiplied by negative psi j plus 1 plus 2 psi j minus psi j minus 1 is equal to e times psi of j. Using the same formula as before, j is equal to 1, 2, and 3. So this is going to give us a piecewise, so not a piecewise, a system of equations with 3 equations. 8h bar squared over ma squared stays at the front because it appears in every single one. And now for j equals 1, we get negative psi 2 plus 2 psi 1 minus psi 0 is equal to e psi 1. For psi 2, we get negative psi 3 plus 2 psi 2 minus psi 1 is equal to e psi 2. And then for j is equal to 3, we have negative psi 4 plus 2 psi 3 minus psi 2. And this is equal to e times psi 3. Once again, from the same logic as before, psi 1, 2, and 3 are the only ones that appear, but we also have psi 0 and psi 4 that automatically implies, and also just from inferencing from the boundary conditions, we get psi 0 has to equal psi 4, and they both have to equal 0, because the wave function has to go to 0 at the ends of the well. Now, rearranging this, with this in mind, we have 8h bar squared over ma squared times our new system, which is going to be negative, and you know what, let's rearrange this, so 2 psi 1 minus psi 2, and then we have negative psi 1 plus 2 psi 2 minus psi 3, and then negative psi 2 plus 2 psi 3. And this equals e psi 1, e psi 2, and e psi 3. I've rewritten this as a vector notation. So rewriting this as a matrix function, we get 8h bar squared over ma squared. Rewriting this as a matrix, we get 2, negative 1, 0, negative 1, 2, negative 1, and then 0, negative 1, 2. And then this is multiplied by the matrix, or the vector of psi, which is now a 3-term vector, psi 1, psi 2, and psi 3. And this is equal to e times psi 1, psi 2, psi 3. So therefore, our H matrix for n equals 3 is equal to 8h bar squared over ma squared multiplied by 2, negative 1, 0, negative 1, 2, negative 1, 0, negative 1, 2. And with that, we are done with part A. Okay, so part B is asking us to find the eigenvalues of our H matrices and compare them with the exact allowed energies. So this is referring to way back in the introduction where Griffiths makes the claim that, as you can see from the example, the allowed energies are the eigenvalues of the matrix H. So this is true, and we are not really proving it. We're sort of just showing you from just this matrix, and very obviously if you look at the H matrices, you can see that sort of these are like diagonalized, sort of, almost. And what you see is that like these eigenvalues apparently give you the energies. That being said, we're not proving this, we're just showing by brute forcing out the math by hand. And the actual proof for why this happens is a lot more complicated, and it gets covered in chapter 3 in very heavy detail. But for now, we're just getting introduced to the idea that the eigenvalues of this H matrix that we've just defined apparently give us the allowed energies. So we're going to solve these by hand. So to solve an eigenvalue problem, I'm just going to go over this very briefly. So you start with H times psi is equal to E times psi, where H is a matrix, psi is a vector, and then E is a constant. And what you do is you rearrange this and you say, okay, I can rewrite this by moving E to the left, and I can rewrite this as H minus E times the identity matrix multiplied by psi is equal to 0, where 0 is a vector, psi is a vector, and I should probably emphasize that these psi's are vectors. And then finally, to solve this, I say that the determinant of the matrix H minus EI has to equal 0 to solve for the eigenvalues. So I'm just going to do this for H1, 2, and 3. So in the H1 case, this is pretty trivial because this is a 1-by-1 matrix. So in this case, H1 minus E times I. The determinant of this is just going to be H1 minus E times I, and this is equal to 0. So if I write this out, then it's 4h bar squared over ma squared minus the energy, and then I is just a 1-by-1, so it doesn't matter, and this is equal to 0, so the energy is equal to 4h bar squared over ma squared. Okay, next, let's do it for the slightly more complicated ones. So for H2, I get that the determinant of this is, let's see, H2 minus EI. So this is going to be, let's copy and paste this down so that I can reference it. Let's split this off. So we get, my matrix is going to be, let's see. The 2's cancel out for the first term, so 9h bar squared over ma squared minus E, and then it's an identity matrix, so the off diagonals, nothing happened to them, so this off diagonal is negative 9h bar squared over 2ma squared. Same thing with this off diagonal, it's just negative 9h bar squared over 2ma squared, and then this term is the same thing, so 9h bar squared over ma squared minus E. This determinant is evidently supposed to equal 0, so I just solved this as a determinant, so AD minus BC, right? So 9h bar squared over ma squared minus E squared minus BC, which is going to be 9h bar squared over 2ma squared. The negatives cancel, this makes a square, and this is equal to 0. I'm too lazy to write this out fully and solve it. You can just plug this into a calculator and solve this on your own, but the valid solutions you get for E are going to be 4.5 h bar squared over ma squared, and then 13.5 h bar squared over ma squared. If you want to solve this on Mathematica, that's very trivial. If you want to do this on Python, in previous problems, I've already sort of shown how to solve basic systems of equations like this using SymPy. It's very trivial, so I'm just going to skip over that because I don't feel like going over it again. These are the valid solutions for the n equals 2 case. Now let's bring out the n equals 3 case, which is going to be the most painful one to do. But if you are using Python like you should be for problems like this, it is also still trivial. My determinant is now going to be, let's see, 16 h bar squared over ma squared minus E, and this term goes across all diagonals, so this goes down like that and then goes down like that, The off diagonals are just 0, so those don't matter. And then we have the negative ones multiplied by the coefficient, so negative 8 h bar squared over ma squared. I'm going to copy paste this and move it down to all these off terms over here, like that. And then now you just have to do a 3x3 determinant. So this isn't the most fun thing to set up. Once again, SymPy is your friend, Mathematica is your friend. I'm not going to bother writing out the full equation, but realistically, this is just a matter of writing this out and finding the determinant, which is up to you. But the resulting energies that Python or SymPy, whatever you decide to use, is going to spit out is going to be something like 4.69 times h bar squared over ma squared, 16 h bar squared over ma squared, and 27.31 h bar squared over ma squared. So in this case, because of the fact that we're finding a determinant, also this has to equal 0, so that's how you solve for e. So the fact that this is a 3x3 determinant, you're going to get a polynomial in terms of e cubed. So if you solve that, you're going to get 3 valid solutions for e, and these are your 3 valid solutions. Now, to compare, the actual valid energies as solved mathematically way back at the start of the chapter are defined as En is equal to h bar squared. Actually, you know what? I'm going to write this. Yeah, h bar squared pi squared n squared over 2m a squared. And if you write this for n equals 1, 2, and 3, what you're going to get is that the actual solutions are somewhere around the line of 4.93 h bar squared over ma squared, 19.7 h bar squared over ma squared, and 44.4 h bar squared over ma squared. So the key pattern here is that if we split our well into just 2 equal parts, this method predicts that there's only a single valid energy, and it predicts it as 4 with the coefficient of 4. That's pretty far off of the actual solution, which is 4.93. But this first energy that gets predicted, if you split into 3 equal parts instead, it goes up to 4.5, which is slightly close to the right answer. If you go up to 4 equal parts down here, then the new predicted first level energy is going to be 4.69. So the higher the number of intervals you split your well into, the more accurate your energy predictions go. And also, in the limit that you split your well into infinite equal parts, which is where delta x goes to 0, you now have infinite valid energies. It's going to predict infinite energies, just like how this suggests that, n can go up to infinity, so therefore there's an infinite number of valid energies, and also the actual valid energies get closer and closer to the correct answer. Because remember, up here, for the second energy, it's 13.5, and then it goes up to 16, which is more closer to 19.7. So in the limit that you go up to an infinite number of equations, these energies go to the actual correct exact values. Okay, finally, or not finally, but in part C, we are going to move on into coding. So we are asked to use a computer to find the 5 lowest eigenvalues numerically for n equals 10 and n equals 100, and then compare the exact energies. So first off, we have to find the general form for our H matrix. So the coefficient at the front is predefined. This is what we already saw before. The coefficient at the front is defined with this formula. What we have to find is the general form for the matrix itself. And hopefully the pattern is pretty obvious. If you look up here, what we find is that, it starts off 2, and then it becomes a diagonal, and then we see that all the off diagonals, the ones directly adjacent are -1, and then the ones farther out just be 0. So following this pattern, you would expect that for n equals 5, you would expect the H matrix to equal, for 5, that's 36, divided by 2, that's 18. So 18 h bar squared over ma squared. And then it's going to be, a 5 by 5 matrix with the diagonals all as 2s. So 1, 2, 3, 4, 5, like that. And then all the adjacents as -1, so -1, -1, -1, -1, -1, -1, -1, -1, and then all the other terms being 0. So 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, like that. And then for the n equals 10 case, it's the exact same thing, but just with 10 of these, 10 rows and 10 columns, but the same pattern, which is that the diagonals are always going to be 2 and the off diagonals are always -1, and then everything else is 0. So if we actually want to find the eigenvalues on Mathematica or Python or whatever, depending on which one you use, which program you use, it'll be significantly easier or harder. Once again, Mathematica sort of trivializes a lot of this, but not everybody has Mathematica, so I will be using Python. In Python, this is significantly harder to code out because Python isn't really optimized for math like Mathematica is, but that's fine. So in Python, for those of you who don't have Mathematica, the primary challenge, your first goal, is going to be actually defining the formula to make this matrix. So I'm going to do that, and I will meet on Python. And once again, just like the last problem, we're going to be seeing some limitations of Python in this problem here. Okay, welcome to Python. So immediately, since I'm working with SymPy, I'm going to import everything from SymPy. So I'm going to start by writing from SymPy import all. Next, I'm going to start my matrix algorithm. So I want to define the general formula matrix. The first thing I'm going to do, so the way SymPy defines matrices is with the matrix command. So basically, it takes matrix, and then it takes a list of whatever, of however many rows you have. So basically, you want to define your 10 rows for your 10 by 10 matrix, and then you want to put them all into a list, and you want to use the matrix command on it. So I'm going to define my list as matrix rows, like this. Now, the next thing I need to do is I need to start adding in the individual rows. So for this, we're going to use an iterative sequence. I'm going to use a for loop. So for A in range, I'm going to say 1 through 11. This is my preferred method. I don't like that the index calls starting from 0 to 9 typically for, if you do like 0, 10. So instead I use 1 through 11 just so I can keep my matrix rows consistent and easy to read. And I'm going to define an empty row. I'm going to call it individual row. And this is going to be equal to just a blank list. So individual row is equal to this. Now I'm going to start adding terms for my individual row. So each row of my matrix has 10 entries. So I'm going to define a second for loop in the first one for B in range 1 through 11. I'm going to say that if it's a diagonal element, then it's equal to 2. So if B is equal to A, so this represents, row 1, column 1, or row 2, column 2, and so on and so on, then I'm going to add 2 to that row. So individual row.append 2, like that. So this is basically saying if it's a diagonal term, I'm adding 2. Next, else if B is equal to A plus 1, individual row.append -1, and then else if B is equal to A minus 1, individual row.append -1. So what this is saying is that for all the off diagonals, I am adding -1 to them. So those elements will always be -1. And everything else is 0, so else individual row.append 0. So basically, this thing is going to add 10 numbers into this individual row list. If it's a diagonal element, it's going to add a 2. If it's an off diagonal, it's add a -1. Otherwise, it's going to add a 0. And then finally, I'm going to insert individual row into my matrix row. So matrix rows.append individual row, just like that. So what this is doing is it's making my individual row, so any given row on my matrix, by using this algorithm, then it's adding this row into the list of total matrix rows. And once I've finished the loop and done this 10 times, I'm going to turn matrix rows into a matrix. So I'm going to say matrix rows, like that. And just like that, I have my diagonal matrix, like this. Now, the next thing we're going to do is we're going to define our coefficient. So to do this, I'm going to define coefficient 10. So coefficient 10. And this is going to equal, so remember the formula, n plus 1 at the top, squared. So 10 plus 1 is going to be 11, so 121, multiplied by the symbol h bar. So I'm going to call this symbols h, because remember, SymPy requires us to define variables with the symbol command. and this is squared. And then this whole thing is divided by 2 multiplied by m, so symbols m, multiplied by a squared, so symbols a squared. So if I print out coefficient 10, this should give me 121 h bar squared over 2ma squared, like that. Okay, good. Now, our actual matrix. So this is going to be n10, and I'm going to call this equal to the coefficient 10, multiplied by matrix rows. And this is going to be subtracted by symbols E. So this is the energy multiplied by the identity matrix, which is called, in SymPy, identity, and then the number of rows and columns. So in this case, it's a 10 by 10, so the command is I10. So this command gives you an identity matrix that is 10 by 10. So now, if I put this out, this should give me this matrix. And now I have to find the determinant for this. So n10 dot determinant is going to be what I'm going to find. And then we want to set this equal to 0 and solve for E. So first off, if I print this out, right? This is going to give me a very complicated thing. And as you can see, this is sort of where we run into the limit of Python, in that it does not work with very large matrices like this particularly well. Look at all the time it took to solve that. So I'm going to say that this is my determinant is going to equal this. And now I'm going to want to set this to 0 and solve for E. So I'm going to set this way. And you know what, just to make sure I know that it's done printing, I'm going to say pretty print determinant. I'm going to stop it from running, and then determinant, yeah. So I'm going to print out the determinant. So we're going to wait the full time so that I know for sure that it has associated the determinant variable with this n10.determinant command. So once again, Python does not work very well with these very long equations. So it has solved it. It has given me, you know, an expression a polynomial expression with e to the 10th, so up to 10th order. Next, we're going to solve for the eigenvalues. So eigens is going to equal solve. I'm going to say this is going to be determinant. And I'm going to solve this for E. So this is going to be solved for symbols E. So the way solve works is it's going to solve whatever equation you give it, and it's going to set that equation equal to 0. So it takes this determinant expression, and it's going to set that equal to 0, and I'm commanding it to solve for the expression for the symbol big E. And I'm going to print out these eigenvalues. So what you see here is that we're getting something called C root of. So remember, SymPy is, as convenient as it is designed to solve for things symbolically. And this C root of is its way of trying to symbolically show that the result we're going to get is going to be the root of this expression. So to get an actual numerical answer, we have to use a command called n. So we're going to say, let's see. So I defined eigens up here as the eigenvalues for each value in eigens. So for a in eigens, I'm going to say I want to print out the numerical solution, n of that. Because it's going to give me all of these C root expressions. I want to find the actual numerical roots. So I'm going to say print out the numerical version of this. And it's going to give me this list. So the first 3 energies, which is the lowest 3 energies, is going to be 4.901 h bar squared over ma squared. And then the next one is going to be, 19.21 h bar squared over ma squared. And then the third one is going to be like 41.8 h bar squared over ma squared. And if you compare that sort of to the original accepted values, these are much closer compared to when we were doing just n equals 3. So if you compare these to the actual true values, these are a lot more accurate to what they're actually supposed to be. For n equals 100, you just do the exact same thing we did here, but we're using a range from 1 to 101 instead of from 1 to 11. Considering how long it took Python to just find the determinant for this, I am not willing to waste time doing the 100 one. You get the general idea. Unfortunately, Python is not made to solve math, unlike Mathematica, which specializes in it. So because of that, the process is a lot more difficult and slower for Python. There's actually a command to directly find eigenvalues for matrices, but it can't handle ones that are this complicated with like all of these coefficients inside of it, with this coefficient thing multiplied by this. It might be able to find an eigenvalue for this matrix, but it's not going to be able to do it if you include the coefficients. So just in general, Python just isn't that good at finding these. So because of that, I'm going to skip the n equals 100 one and just stick with n equals 10. And with that, we will move on to part D. In part D, we are asked to find the eigenvectors. So to do this, we're going to start by writing out our equation from earlier. So for the n equals 1 case, we have h minus e1, because there's only one energy for the n equals 1 case, times the identity matrix I, and this is multiplied by the psi1 vector. And this is equal to 0. So our H matrix for the case where n is equal to 1 is 2h bar squared over ma squared multiplied by the 1 by 1 matrix, which is just 2. This is going to be subtracted by E1, which is going to be 4h bar squared over ma squared. So this is the energy that we approximated from the n equals 1 case, and then this is multiplied by the 1 by 1 identity matrix, which is just going to be 1. And then this whole thing is multiplied by psi1, which is going to be a 1 by 1 matrix again, this time just psi1. And this is going to equal 0, or the 1 by 1 matrix of 0. So immediately, hopefully you see that these two just instantly cancel out to 0. So what we get is 0 times psi1 is equal to 0. So what this means is that psi1 is arbitrary. It can be anything. That being said, we have this additional condition, which is that the magnitude of psi squared has to be normalized. 1 has to equal the integral from 0 to a of the magnitude of psi squared dx. This is a condition that will affect what psi1 actually is, but we have a bit of a problem, which is that psi1 in this case represents not the first wave function for energy, but rather it represents the wave function at the point x1. Because remember, if we split our well into 0, x1, and then a, psi1 is the wave function at x1. So we have to somehow divide our wave function psi into intervals so that psi1 appears in this resulting integral expression. And in general, when you're trying to approximate an integral by dividing the resulting region into equal intervals, typically n+1 divisions, you use one of two different rules to approximate the division. They are called the trapezoidal rule and also Simpson's rule. So I am going to copy and paste them down here. Typically, you want to use Simpson's rule because it is more accurate, but it can only be used when n+1 is even. So for Simpson's rule, this can only be used when n+1 is even. So if n+1 is odd, we are forced to use the trapezoidal rule. In this case, because n is 1, 1 plus 1 is 2, that's even, we can approximate using Simpson's rule. So the integral from 0 to a of the magnitude of psi of x squared dx is equal to 1, and via Simpson's rule is approximately equal to a over 3n plus 1, so n plus 1 is 2 times 3 is 6, multiplied by, and this pattern is 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, and then 1, ending at 1. So in this case, we have x0, xn, and xn plus 1, because n is just equal to 1. So this is going to be psi 0 squared plus 4 psi 1 squared plus psi 2 squared, like that. So once again, what I'm doing is I'm following Simpson's rule. So x0 is the first term, and then we're jumping straight to xn, because remember, in this case, n is just 1, so we're jumping straight to this, and then we're doing this. This is approximately equal to 1. So in that case, if we add everything together, remember psi 0 and psi 2 have to equal 0 because of the boundary conditions. The wave function has to go to 0 at either end of the well. Therefore, this is equal to a over 6 multiplied by 4 psi 1 squared. Therefore, simplifying this out, this is going to be 2a over 3 times psi 1 squared. This has to equal 1. Move everything over, we get psi 1 squared is equal to 3 over 2a, or psi 1 is equal to the square root of 3 over 2a. In which case, our psi 1 vector is therefore just the 1 by 1 vector of the square root of 3 over 2a. Now, let's move on to something that actually uses matrices, the n equals 2 case. So in this case, we have, once again, h minus, and in this case, we actually have 2 cases, because remember, because of the fact that we've gone up to n equals 2, there are now 2 approximated energies, E1 and E2. So we're going to have 2 different vectors that we actually have to solve for. Let's start with E1, so E1 times the identity matrix times the vector psi 1 is equal to the vector 0. So the H matrix, in the case where n is equal to 2, according to our formula from above, is 9h bar squared over 2ma squared. And this is going to get multiplied by our matrix 2, 2, negative 1, negative 1. And this is getting subtracted by the first predicted energy, which is, in this case, instead of 4, it's going to be 4.5 times h bar squared over ma squared. Because remember, the energies will change. They will get more accurate as n gets higher. So this is more accurate compared to the true version of 4.9. 1, 1, 0, 0 for our 2 by 2 identity matrix. This whole thing is then multiplied by psi 1, psi 2 for our 2 by 1 vector. And this is equal to 0, 0. If you then multiply this out and get everything together, this matrix ends up equaling 4.5 h bar squared over ma squared for term 1, negative 4.5 h bar squared over ma squared for term 2, negative 4.5 h bar squared over ma squared for term 3, and then 4.5 h bar squared over ma squared for term 4. This is getting multiplied by psi 1, psi 2, and this is equal to 0, 0. And from the symmetry here, hopefully you see that the 2 equations we get are actually the exact same of each other, just with one being like the negative inverse of the other. So the resulting equation that we're just going to get is just going to be 4.5 h bar squared over ma squared times psi 1 minus 4.5 h bar squared over ma squared psi 2 is equal to 0. The second equation is going to be negative 4.5 h bar squared over ma squared times psi 1 plus 4.5 h bar squared over ma squared times psi 2 is equal to 0. That one's just the negative of this one is exactly the same. So we cancel out all the like terms. What we get is just psi 1 minus psi 2 is equal to 0, or psi 1 is equal to psi 2. Therefore, our vector is actually just psi 1 comma psi 1. Next, let's use our approximation rules from above. This time we're going to be using the trapezoidal rule because remember, n plus 1 has to be even for us to use Simpsons. So in this case, n plus 1 is 3, which is odd, so we're going to be using the trapezoidal rule. Let me just extend my canvas again. So at this point, if we're using the trapezoids rule, then we have the integral from 0 to a of magnitude psi squared dx is roughly equal to a over 2 times n plus 1, which is going to be 3, which is going to be a over 6 again, this time for the trapezoidal rule. And then we're multiplying by psi 0 squared plus, in this case, all the middle terms are just 2. So 2 psi 1 squared plus 2 psi 2 squared, and then plus psi 3 squared. So once again, via boundary conditions, psi 0 and psi 3 go to nothing. So this is equal to a over 6 times 2 psi 1 squared plus 2. Psi 2 is equal to psi 1, so we just repeat this as psi 1 squared, rewrite it that way. In this case, we get 4a over 6 psi 1 squared, or simplifying 2a over 3 psi 1 squared. Which means that since this is equal to 1, then psi 1 squared is equal to 3 over 2a, which means that psi 1 is equal to the square root of 3 over 2a. In that case, our vector, psi 1, is going to be root 3 over 2a and root 3 over 2a. Next, in the case of E2, we have H minus E2 times the identity matrix times psi 2 is equal to the 0 vector. In this case, we have 9h bar squared over 2ma squared times 2, -1, -1, 2. This time minus our predicted E2 value, which is going to be 13.5 h bar squared over ma squared times 1, 1, 0, 0. And this is multiplied by psi 1, psi 2. This is equal to our 0 vector. If you multiply this out, or if you multiply this out and add these two matrices together, you're going to get that everything is going to just be the same, -4.5 h bar squared over ma squared, and every term here is going to be equal to that. So I'm just going to copy paste this. And just get rid of that extra little thing I accidentally included. There we go. And then this is multiplied by psi 1, psi 2. This is equal to 0. Once again, we're getting two of the same equation. In this case, it's just going to be -4.5 h bar squared over ma squared psi 1 minus 4.5 h bar squared over ma squared psi 2. This is equal to 0. Therefore, negative psi 1 minus psi 2 is equal to 0, or psi 1 is equal to negative psi 2, or psi 2 is equal to negative psi 1. So then our vector is therefore going to be psi 2 vector is equal to psi 1 and negative psi 1. In that case, if we're squaring everything via trapezoid rule from before, we're still going to get the same result. Psi 1 is still going to be equal to square root of 3 over 2a. So that means that psi 2 vector is actually equal to square root of 3 over 2a and negative square root of 3 over 2a. For n equals 3, we're going to have 3 vectors. We're going to have to solve a system of 3 equations, blah, blah, blah. Honestly, I'm a little bit too lazy to do that, considering that we already sort of know the general idea behind this. So I'm going to go straight to the Python method of solving the n equals 10 system for the first energy. So I will see you on Python. Right, welcome to Python. I have kept all the code from the first, from part C, when we ran sort of the n equals 10 case for the matrix. So this is our matrix, our 10 by 10 matrix that we have, that we're supposed to have for H. We have the coefficient down here defined, and we have our n10 matrix defined. So this is, n10 is going to be sort of our matrix multiplied by the coefficient at the front. This is all defined from before. The next thing we're going to have to do is we're going to have to define E1. So we have E1 from part C. It was defined as 4.901 h bar squared divided by ma squared. So we solved for this in part C. That was the whole point of all the code we did in part C. Now we're going to define our new n10 as basically just replacing the symbol E with our term E1. So I'm going to redefine n10 with the coefficient times 10 times the matrix. This time, instead of minusing E times identity, it's E1 times the identity. So basically, all I'm doing is just I'm redefining the matrix that we had from part C, this time with an actual value for E1 instead of just E1 being just the variable E. Next, I want to multiply this by my psi vector. So in this case, psi is going to be a 10-row vector. I am lazy and I don't want to write a for loop for that, so I'm going to brute force it by just writing out, using SymPy, the matrix, P1, P2, P3, P4, P5, P6, blah, 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 blah. And next, I'm going to do, what I'm going to do next is I'm going to take their product. So I take this, and I do product is equal to n10 multiplied by psi. So this is going to give me my system of 10 equations. If I run this, I'm going to get, oh, I forgot to print it. If I run this, I'm going to get this product. So our goal is to pretty much do what we did earlier and rewrite each of these psi n terms in terms of psi 1. So our goal is therefore to solve each of these equations in terms of psi 1, then replace every instance of the variable of interest in all of these remaining equations down below. Now, realistically, this whole process technically should be able to be done in a single line of code just by using sort of the eigenvalue function. But once again, we run into the problem, which is that Python doesn't really work well with these large problems for math. So because of that, we kind of have to do it the brute force way, which is doing it this way. So in order to actually solve this, the code is somewhat complicated. I will go as slow as I can, but realistically, once again, I am not a coder. I'm not good at explaining code like I am in physics. So just know that my general goal is to basically write a for loop, which is going to solve it's going to solve a given equation in this list, and it's then going to take that equation. It's going to solve this in terms of like for example, this first line is going to solve P2 in terms of P1. So P2 is going to be equal to something times P1. Then it's going to replace every instance of P2 it finds underneath here with whatever it solved for P1. And then it's going to go into the next line, and it's going to do the same thing, but for P3 instead, solving P3 for P1, and then replacing every instance of P3 for P1, and then repeating all the way until it finishes everything here. And then I'm going to write all of that onto a custom list I'm going to call psi list or P list. I'm going to call this list. I'm going to define it as P1 because that's what we're solving for. And then I'm going to call the rest of the terms 2, 3, 4, 5, 6, 7, 8, 9, 10, like that. So that way, eventually I'm going to write all of the P terms in terms of P1. I'm going to write them to this P list. All right, so our for loop. So the first thing we're going to do is I'm going to define A for range 0 to 9. So the reason why I'm defining A in range from 0 to 9 is I want to solve every equation in this list. But you might be asking, okay, there's 10 equations in this list. Why am I only doing 9 of them? And the reason is because we already have psi 1. We have psi 1 just as itself. So we actually only need psi 2, 3, 4, 5, 6, 7, 8, 9, and 10. So if you look at this, we're going to solve the first equation for psi 2. That's going to let us solve the second equation for psi 3. That's going to let us solve equation 4 for psi 4. And then psi 5, psi 6, 7, 8, 9, and 10. All the way up to here. We don't actually need this final equation. So we're just going to ignore it and do for A in range 0 to 9 instead. Next, what I'm going to do is I'm going to define my variable of interest. So in that case, our variable is going to be P and then plus the string of A plus 2. So A starts at 0, but my psi variable that I'm solving starts at 2. Because remember, the first term I want to solve is going to be P2. So the way I define it is P plus the string of A plus 2. That way, it starts at P2, and it goes, so this range goes from 0 to 8, because it ends right before this end term. So this range is going to call A for A equals 0, 1, 2, 3, 4, 5, 6, 7, and 8. So because of that, my variable is going to solve from 2 all the way to 10. So P10 is my final one, so that's why I'm doing it this way. Next, I'm going to solve. So I'm going to write out a solution. I'm going to say solution is equal to solve product index A in terms of symbols, the variable I define here. So remember, product is my matrix equation that I defined way earlier up here. Product is this thing. So I'm going to solve for A in range 0 to 9. So I'm going to solve in this loop, basically, the first equation. So for the A equals 0 case, I'm going to solve the 0th index, which is this equation. I'm going to solve it for the variable of interest, which for the A equals 0 case is going to be P2. So I'm solving this for P2. And after that, the next thing I'm going to do is I'm going to substitute the resulting solution into my P list, which is the actual result I want. So P list of A plus 1, because remember, I'm starting on the P list, I start at the index of 1 instead of at index 0, because index 0 is already defined as P1. So if A is equal to 0, then P list is going to substitute into index 1 instead of index 0. So it's going to start here, and it's going to substitute this term with whatever I got here. And the reason why the 0 here is because Solution, this solve command is going to return a list for me. It's going to return a list of a single item. So I do solution index 0 so that I actually can call that item. Because if I don't do solution 0, it's going to call a list, and that's going to put a list inside my list. I'm going to get like a tuple or something. So because of that, I'm doing solution index 0 to reference, the actual solution itself. Because once again, solve returns a list. So I need the item in the list, so I'm calling solution index 0. Right. Next, the next goal is I have to replace every instance of P2 in this product list with its definition in terms of P1. So I have to do a second for loop. I'm going to say for B in range. And in this case, it is going to be A from A to 10. Because I only have to go from whatever one I'm going. So if I'm solving this first term here, then I obviously have to replace everything. But like after that, I solve for this second term. I don't have to pay attention to the first one anymore. I just replace everything underneath it. So B is going to start in range A and is going to go all the way to 10. So I'm substituting everything. And then what I'm going to do is I'm going to replace prod B with a substitute command. So I'm going to write this out. So prod B is basically, whatever index I'm calling for B. And so basically everything underneath my equation of interest, I'm going to use the subs command, which substitutes a variable for another. So it's going to substitute my symbol of interest, which for the first case is going to be P2 right here, right? And it's going to substitute every instance of P2 it finds with the solution that I just found, solution 0. So this is P2 equals something P1, right? So I solved solution here is the solving of P2 in terms of P1. I'm going to replace that solution down here with all of the instances of P2. So all of these P2 instances that appear are going to get, so there's only two here, P2 and P2 right here. These two are going to both get replaced with their definition in terms of P1. And this for loop basically just goes down the entire list, and it's going to replace every instance of P2 that it finds with P1. Then A is going to repeat again. It's going to go to A equals 1, and I'm going to solve for P3. Everything's going to happen again, and then I'm going to go down the list and replace every instance I find of P3 with its definition in terms of P1, blah, 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 so on, so on, so on, so on. And now, if I write out my P list, I now have a vector. I now have a 10 by 1 vector where all of the P vectors are now purely in terms of P1. So now I can bring this back into my paint application, and I can solve this using either Simpson's rule or trapezoidal rule. In this case, it's n plus 1 is 11, so I have to use trapezoidal rule. So I will see you back on paint. Okay, so I'm going to be using trapezoidal rule to write out this normalization statement. So 1 is equal to A over 2 times 11, which is going to be 22, and then psi 1 squared plus 2 times, let's see, psi 2 is going to be 1.92, psi 1 squared plus 2 times 2.68, psi 1 squared plus 2 times 3.22, psi 1 squared, plus 2 times 3.51 times psi 1 squared, plus 2 times 3.51 times psi 1 squared, plus 2 times 3.22 times psi 1 squared, plus 2 times 2.68 psi 1 squared, plus 2 times 1.92 psi 1 squared, plus psi 1 squared. So there's a bit of a very nice symmetry going on here. Let me just make sure that I have 10 terms. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right. So now that I have this, it's just a matter of solving it. So I'm not going to bother writing out everything. The resulting solution you're going to get is that psi 1 squared is going to equal 0.16 over A. So then if I take the square root of this, then psi 1 is going to equal 2 over 5A. So in that case, you would then take this and you would plug this back into your expression, psi 1, psi 2, psi 3, psi 4, psi 5, psi 6, psi 7, psi 8, psi 9, psi 10. you would plug this back into your matrix, and you would replace, you know, all the instances, because I'll take a screenshot of this from before. Our actual matrix that Python gave us looks something like this, so it's just a matter of multiplying all these terms out, multiplying them onto psi1, and then replacing everything. And with that, we are done with this problem.